In the days following 3I Atlas's perihelion passage, data from multiple solar observatories continued to reveal a dynamic and unpredictable environment. The solar wind, heavily disturbed by recent CMEs, carried fluctuating magnetic fields and variable particle densities through the inner solar system. As this stream expanded outward, it interacted with the comet's residual tail and coma, allowing researchers to study plasma behavior at scales rarely observed. High-resolution modeling from NASA's Heliophysics division indicates that portions of the CME-driven plasma front likely overtook 3I Atlas even as it began its outbound trajectory. This overlap provides a valuable test case for understanding how charged particles and magnetic turbulence affect the structure and chemical composition of a comet's atmosphere. Changes in ionization rates, observed through UV-sensitive instruments, suggest that even after peak solar exposure, secondary reactions continued to drive subtle emissions within the coma for several days. Meanwhile, astronomers using the Solar Orbiter's SPICE spectrometer detected faint traces of volatile compounds, including carbon monoxide, ammonia, and cyanogen, that may have been newly liberated during the CME encounters. These molecules, once frozen in the nucleus, were likely exposed by rapid erosion or fragmentation on the surface. Combined with photometric data, the chemical signatures help reconstruct how the comet's outer layers responded to intense space weather, offering clues to the material composition of interstellar bodies. The irregular morphology of 3I Atlas also remains a focus of study. The uneven coma structure and faint intermittent tail suggest that internal cohesion within the nucleus may have been compromised. If the nucleus experienced differential heating or repeated plasma impacts, localized fractures could have opened, releasing gas and dust in bursts rather than steady flows. Several modeling teams are now comparing this behavior to that seen in past comets affected by solar storms, such as Comet Encke during the 2007 CME interaction. As 3I Atlas continues on its outbound leg, ground-based telescopes will regain visual access as solar elongation increases. The Very Large Telescope and Subaru Observatory have scheduled monitoring sessions to track any residual activity or fragmentation events. Infrared sensors will be particularly important in identifying fresh dust trails that might still reflect sunlight long after the main outburst subsides. These efforts will allow scientists to determine whether the comet's brightening event marked a one-time plasma-induced flare or if periodic outbursts persist as it cools. At the same time, space weather monitoring agencies are coordinating closely with astronomical teams. The same magnetic regions on the Sun that triggered the earlier CMEs are expected to remain active for several weeks. Each rotation of these regions toward Earth presents a renewed chance for high-energy events, making real-time observation crucial. The study of 3I Atlas serves as a parallel investigation. While not dangerous itself, it acts as a marker for how deeply solar activity can reach into the inner solar system and affect smaller bodies. Historical comparisons are already being drawn between the current solar cycle and Cycle 23, which produced the well-documented 2003 Halloween storms. While today's solar maximum has not yet reached those levels, the current data indicate comparable magnetic complexity. For engineers and mission planners, these observations inform how future spacecraft might respond under similar plasma conditions. If the interaction between CMEs and cometary material can produce such strong optical and chemical signatures, it may also impact satellites, probes, and even the interplanetary environment around crewed missions. Looking further ahead, scientists emphasize that 3I Atlas represents more than an isolated event. It is the third known interstellar visitor to pass through our solar system, after Oumuamua in 2017 and 2I Borisov in 2019. Each object offers a snapshot of material formed beyond the Sun's gravitational influence. Studying how these objects react to solar energy and plasma provides insight into conditions in other planetary systems. The unusual brightening of 3I Atlas, combined with its stable trajectory, helps refine models of interstellar body composition, surface strength, and volatile content. By late November, ESA's JUICE mission is expected to release its first processed images and spectral data. Early internal reports suggest that the comet's brightness has already declined to pre-perihelion levels, but detailed analysis will determine whether new jets or secondary outbursts occurred during its departure. The mission's findings will be cross-referenced with ground-based spectroscopy and photometry, creating a comprehensive data set that could shape the next decade of comet research. For now, the scientific community's consensus is cautious but clear. 3I Atlas has provided one of the most detailed natural experiments in solar-comet interaction ever recorded. The alignment of its perihelion with a major CME sequence offers direct observational evidence of how solar plasma can alter the behavior of small bodies, both visually and chemically. As Earth continues to rotate beneath an active sun, these findings also highlight how interconnected solar activity, near-space conditions, and interstellar visitors truly are. The coming weeks will reveal whether new CMEs emerge from the same solar regions and how Earth's magnetosphere responds. Whether through auroral displays, radio disruptions, or subtle geomagnetic variations, the echoes of 3I Atlas's encounter may continue to ripple through the inner solar system, a reminder that even distant wanderers are bound, however briefly, by the forces radiating from our own star.
A mysterious interstellar visitor is racing through our solar system, 3I Atlas, officially cataloged as C-2025N1. This object has captured the attention of scientists around the world, not only because of its alien origin, but also because of its unpredictable behavior as it approaches the Sun. What started as a faint, icy body entering the outer regions of our solar system has quickly evolved into one of the most fascinating and potentially revealing cosmic events of this decade. When astronomers first spotted 3I Atlas, it seemed to follow the expected path of a long-period comet, a distant traveler drawn temporarily into the Sun's gravitational field before vanishing back into interstellar space. But as it approached the inner solar system, something strange began to happen. Its brightness began to rise far faster than models predicted, and within days, it became one of the most dynamic and unpredictable objects in the sky. Unlike ordinary comets that gradually glow brighter due to sublimation, the process where ice turns directly into vapor under solar heat, 3I Atlas showed erratic surges of light. These were not smooth increases, but sudden spikes, as though something within or around it was violently reacting to the solar wind. Telescopes observing it in different wavelengths confirmed that these surges were not just dust reflections, but involved intense bursts of ionized gas. Researchers began to question whether this was just an ordinary comet or something more, a remnant of another star system that carries properties unlike anything born around our Sun. Data from its orbital path confirmed what many suspected. 3I Atlas did not originate here. Its hyperbolic trajectory indicated it was moving too fast to be gravitationally bound to the Sun. In other words, it came from beyond, an interstellar visitor like Oumuamua in 2017 and 2I Borisov in 2019. Unlike those two, however, 3I Atlas has provided a far clearer look at how such bodies behave when exposed to the intense energy of a solar system they weren't born in. Every observation gives us clues about what kind of material forms in distant planetary nurseries and how it reacts under alien conditions. As 3I Atlas drew closer to the Sun, the solar wind intensified. Coronal mass ejections, powerful bursts of plasma and magnetic fields from the Sun's surface, were recorded moving toward its trajectory. The timing couldn't have been more dramatic. While Earth experienced minor geomagnetic disturbances, 3I Atlas was directly in the line of this storm. The collision between a CME and the comet's fragile atmosphere produced spectacular results. Instruments from the Solar and Heliospheric Observatory and ESA Solar Orbiter captured streams of charged particles wrapping around the comet's coma, twisting its tail and causing it to glow unevenly. For several hours, 3I Atlas appeared to shimmer like a living entity, brightening, dimming, and flaring again in unpredictable intervals. For scientists, this was a once-in-a-lifetime opportunity. The encounter offered a real-world experiment on how solar storms affect cometary matter. Normally, such interactions are mild, but 3I Atlas was struck by a high-energy plasma wave at close range. Spectrometers detected spikes in ionized oxygen, carbon, and sodium, suggesting rapid disintegration of surface ice and dust layers. The shock wave from the CME compressed the comet's magnetic environment, creating miniature aurora-like effects within its coma. These interactions revealed how magnetic turbulence can tear through frozen bodies traveling through space. It's not only a spectacular event visually, it's also essential for understanding how solar radiation shapes comets, asteroids, and even planets over time. Observatories across the world, including the James Webb Space Telescope, Hubble, and Subaru in Hawaii, all turned their gaze toward 3I Atlas. They coordinated observations in visible, ultraviolet, and infrared light. The result? A complete dataset showing how material ejected from the comet evolved as it traveled outward. The data suggested that large chunks of dust and ice may have separated from the nucleus, forming secondary tails. One tail appeared dust-rich and curved, while another, composed of ionized gases, pointed directly away from the sun, glowing faint blue under solar ultraviolet radiation. Unlike 2I Borisov, which behaved much like a typical comet, 3I Atlas displayed highly unusual volatility. Its internal structure might contain compounds that are extremely sensitive to temperature changes, possibly hydrocarbons or exotic ices never before detected in our solar system. Some scientists have even proposed that 3I Atlas could be the remnant of a disrupted planetesimal, an object that once orbited another star before being ejected by gravitational interactions. If true, this means the comet carries raw material from an alien solar system, frozen for billions of years.